Hello everyone, my name is Jiemei. I'm a second-year PhD student from University of Washington. I'm happy to present our project, Video-Based Hierarchical Species Classification for Longline Fishing Monitoring. This project is sponsored by NOAA.
I will cover these 5 parts one by one. First, it's the introduction. I will talk about the traditional model for the image classification task. AlexNet is a milestone in the image classification task, which was proposed in 2012. It uses the softmax function as the last layer of the model so that given one input image, the model can predict probabilities over 1,000 classes. We call this kind of model flat classifiers. Next, I will introduce our dataset and task, on which traditional flat classifiers cannot be directly used. We propose a new dataset for hierarchical species classification. Our data is videos from longline fishing, and for each frame, we manually labeled bounding box locations, track IDs, and hierarchical species names. The figure on the right is an example of raw frames. We can see during longline fishing the fish is hooked on the fishing line, and a fisherman pulls up the fish from the water. Here is the data distribution among different species, and data split for training and evaluation. The left figure is a track-based data split, and the right figure is a frame-based data split. We have 3,021 fish, and about 190,000 frames in total. We use about 80% for training, and 20% for evaluation. Our task is hierarchical species classification. Here's the hierarchical structure of our dataset. There are 2 levels. The first level has 6 groups, and the second level has 31 species in total. So traditional flat classifiers cannot be directly used on our task. Next, I will talk about our model design for our hierarchical species classification task. Our model is image-based training. Here is the input image, and ResNet 101 is our backbone to extract image features. From one middle layer, we get the green feature map for group classification, and that feature will be input to head 1 for group classification, and head 1 will output probabilities over 6 groups. Also, we get the yellow feature maps for species classification, and this feature map will be input to other 6 heads for species classification. From head 2 to head 7, each of them will output the probabilities over species under each group. The output from these 6 heads will also multiply with the 6 group probabilities from head 1 to get the final probabilities over 31 species. Because we use the softmax function in each head, the summation of these 2 equations is 1, which makes sure the output from each head can represent probabilities. Loss 1 is the traditional cross-entropy loss for training classifiers, where Y1i is the ground truth label for level 1, and Y2i is the ground truth label for level 2 within one specific group. But we propose loss 2 for hierarchical species classification, where Y2i' is the ground truth label for level 2 among 31 species. Given one input image, loss 1 can only train 2 heads, while loss 2 can train all heads. As a result, loss 2 enables more efficient training, and our model architecture enforces the hierarchical structure by using multiplication operations. Next, I will introduce the experimental results of our proposed model on our datasets. For fair evaluation, we train and evaluate our model on track-based data split. It means the individual fish in evaluation are totally different from training. Scheme 3 is our full model, Scheme 2 and Scheme 1 are ablation studies. Scheme 2 replaces loss 2 with loss 1. Scheme 1 further removes multiplication operations. We use one flat classifier as our baseline, which shares the same backbone with our model. But there is only one softmax layer, so this baseline can only output probabilities over 31 species. Although we use image-based training for our model, we use video-based inference. Specifically, given one track, we average confidence scores among 31 species to pick one species as the predicted species for this track. This inference method is represented as video in the table, and video star represents another video-based inference by using a majority vote. We evaluate our model on level 1 accuracy and level 2 accuracy. A, B, and C represents 3 different methods how to get level 2 predictions. More details can be found in our paper. For method C, it allows the predictions to stay at level 1 if the final confidence score is lower than a threshold. From the table, we can see that our model can achieve a much better performance than the traditional flat classifier. Here is the detailed level 1 accuracy of our model on our hierarchical dataset. We can see our track-based inference can achieve higher accuracy than image-based inference, obviously. Here is the detailed level 2 accuracy of our model. Here is the percentage of stopping at level 1 when using method C for inference. We can see most tail species predictions are stopped at level 1, which results in higher overall accuracy. This is because tail species have fewer images for training level 2 heads but comparably more images for training level 1 heads. Finally, are our conclusions. We propose a public hierarchical dataset. We design a model for hierarchical species classification. In our model, we use multiplication operation to enforce the hierarchical species structure. We propose an efficient training strategy with loss2. We also propose video-based inference to improve the performance. And our model outperforms the baseline dramatically. For the long-tail distribution problem, we found our inference method C, which we call hierarchy prediction, improves accuracy on tail species a lot. Thanks for watching.